At Naftali Muhumza Medical Sciences. In this session, we are diving into gas chromatography, where we are going to look at the definition, its purpose, the principle, instrumentation, and then application of this gas chromatography. Previously, we have looked at the calculations and HPLC. And if it is your first time, please, you're reminded to subscribe, like the video, and share to many others. So, as its name suggests that it is gas chromatography, we call it gas chromatography because the mobile phase. So, before we look at its definition, its purpose or use, we are using it to quantify, to separate, identify, and quantify volatile substances. So here we look at using volatile substances or volatile compounds, and those compounds which can be made volatile, and other compounds which can be made volatile. There are those which are not volatile, but they can be made. And what is the meaning of the word volatile? Volatile, it means these substances can be easily be vaporized or turned into gas even at room temperature. So we can completely turn them into gaseous state when subjected to high temperature under gas chromatography. So that is the purpose of using. We separate, is responsible for separation, identification, and quantification of volatile substances and those which can be made volatile. And we said we call it gas because we are going to see under the principle the mobile phase used is we use a carrier gas. And because the mobile phase is a gas, that's why we refer to as gas chromatography, whereby the carrier gas can be either helium, it can be nitrogen, we can use other gases like argon, and sometimes hydrogen. So these are four gases which we can use as carrier gases or mobile phase in the gas chromatography. And why do we prefer these ones? We are going to see its properties later, whereby this gas must be inert, that is unreactive, should have high density, should be free from any air or water droplets, and should be compatible with the detector system which we are going to use. And they should be thermostable, that is, they should be stable in high temperatures. Those are the inert gases we are using as carrier gas in mobile phase. So we are going to see the mixture, the sample containing different components to be separated, which are volatile, are going to be carried, or the eluent is going to be these gases which are inert. We are saying that these gases must be inert. Inert means unreactive. They should not be able to react with any other substance in the stationary phase. So after knowing the mobile phase, the stationary phase under this gas chromatography, here we are going to use, it can be a liquid, which is the most commonly used, or it can be a solid. That's why we shall find that gas chromatography is categorized into two. It can be gas liquid chromatography, or it can be gas solid chromatography. So that is the two ways or two types of gas chromatography. Gas, liquid, whereby the mobile phase remains as a gas, then the stationary phase is a liquid, which is most commonly used. This is the most common used and the preferred, but we can also have the solid. So after understanding these two, the mobile phase and the constituents of the stationary phase, now we can look at the principle, whereby the principle is stating that when the sample is injected into, so if I inject the sample which is containing volatile substances into this carrier gas which are inert with high density and thermostable, so when they are injected at a temperature which is greater than 50 degrees centigrade to that of the stationary phase or to that of the column, this sample within the injector port, it is going to be vaporized. After being vaporized, it is injected into a coiled stationary phase. This coiled column is the one that contains the stationary phase, and if substances which are non-volatile are going to be eluted faster and will be detected by the detector. So we are saying the carrier gas containing vaporized sample, because we are using temperature greater than 50 to that of the column. So after being vaporized, it is injected into the column. This coiled column is containing stationary phase, and this stationary phase can either be a non-volatile substance. It can be volatile, and we are going to see that substances which are volatile are going to be eluted faster and will go into the detector system, whereby will be displayed on the recorder. So if the stationary phase we are using is the liquid which is non-volatile, means the way of separation is going to be partition, but if it is a solid, the separation is going to be by adsorption. Partition, what do we mean? We normally say in chromatography that like dissolves like. So if we are interested in separating volatile substances, the liquid which is coated on the silica or any stainless steel column is going to be non-volatile. So because it is non-volatile, it is going to attract the volatile, and the non-volatile, and those which are volatile are going to move faster, and they will be able to be eluted and detected by the detector system. That is what we call partition. Then adsorption, we shall see substances which are polar. If we are using a stationary phase which is polar, so substances which are non-polar will pass through and will not interact so much with the stationary phase. Then which are polar are going to be interacting. So the thing we should understand is that the like dissolves like. If you are using a stationary phase which is non-polar, meaning the non-polar substances are going to be eluted slowly, whereas polar are going to pass via faster. And when we are using the gas, the liquid, is that if the liquid is non-volatile, meaning substances which are volatile are going to be eluted faster. So the retention time will be lower compared to those which are non-volatile. That is the principle behind it. So the instrumentation, we are seeing we need a gas cylinder, and this gas cylinder is containing these inert gases or unreactive gases. Then there is what we call, this is the pressure controller and flow rate controller. So we have the pressure controller, at the same time we have the flow rate controller. So when the gas is injected under pressure from the gas, this one is going to regulate the kind of pressure we are going to use. Then it passes through this valve which determines the flow at which the carrier or the mobile phase we need to use. Then it is taken into what we call the column. This one is the column. Actually, this is the oven, then the column is this. And after being taken, when this mobile phase containing these inert gases which we have listed, like helium, which is commonly used, like nitrogen, like argon, these gases, we said they are inert. So when they are injected within the column, they pass through what we call the injector port. This is the injector port. So, and this is the syringe, or it can be an automatic sampler. Even an automatic sampler can be used. And this one is injecting in the sample mixture. So here, this one contains the sample mixture, which we want to identify, separate, and quantify. So the function of the carrier cylinder is the one that holds the mobile phase, which is the carrier gas. The function of the pressure controller is to regulate the amount of pressure we are running our gas chromatography. Then the flow rate determines at which flow we need per minute. Is it 1.3 per minute, mils per minute? So we shall determine it by the flow rate controller. Then, so this was the first one. We have the second, the third. The fourth is the syringe or the automatic sampler, which injects the sample to be separated. But we are saying this syringe is connected to the injector port. And this injector port should be, its temperature should be greater than 50 to that of the column. What do we mean? If the column temperature is 50 degrees centigrade, this one should be 100 degrees centigrade. Why? Because we want to make sure that this sample, which contains the substance to be separated, is vaporized. So within the sample pot, the importance of maintaining temperature higher than that of the column is to enable vaporization of the sample, so that by the time it is meeting these inert gases, which are carrier gas, and we are calling it the mobile phase, it is already in gaseous state. That's why we keep the temperature at least 50 higher than that of the column, which is coiled. So after vaporizing the sample, it meets with the carrier gas and is transported into the coiled. So we are seeing that this column is highly coiled. And the column can either be containing, the way we have seen it in the principle, it can be made of a liquid, which is the most commonly used, or it can be made of solid. It can be coated with solid. And these columns, they are put in the oven. Why do we put them in oven? To maintain high temperature. Because we run it at temperature between 50 degrees centigrade to 450 degrees centigrade, depending on the detector system and the kind of the sample we are separating. But mostly it ranges between 150 to 450. But we normally start with 50, then we increase, every minute we increase by 10 until we attain the stable temperature we want to use. But for substances which are simple, we can maintain the temperature at the same rate. So one thing we need to know is that this gas chromatography, the stationary phase in the column needs high temperature, that is 50 to 450 degrees. And how is it maintained? It is maintained by putting it in what we call the oven. This is the column oven, which makes sure to regulate the temperature at the temperature we require to run our gas chromatography. And there are two types of column. So if I have column can either be packed or it can be capillary or open tube. The packed column, this one is less effective. Its length is between 2 to 6 meters. It has internal diameter of 2 to 4 millimeters. This is the internal diameter. And it is always packed with like silica or any other stainless steel. One thing we should remember that this column is either made of stainless steel or glass. So these are the two ways we can find this column. It is made up of either stainless steel or it is made up of glass. But it is of two types, whereby we have said this one is less efficient compared to capillary or open tube. You can call it capillary or open tube, whereby capillary, its length is between 10 to 100 meters. So that one, you see, it is very long. And its internal diameter is between 0.1 to 0.5 millimeters. That is the internal diameter. And this one, that's why you find capillary is preferred to the packed column. Why? Because capillary is more efficient than the packed column because of these reasons. And the capillary is made up of either silicon or with glass beads or with diatomaceous earth. So you can find the capillary coated with, can be coated with the diatomaceous earth or glass beads or silicon or silica gel. Then on top of it, it is now covered by non-volatile liquid or any other solid substance depending on the type of chromatography. But as we said, the most commonly used is gas liquid, whereby the stationary phase is volatile, non-volatile substance. So this is what we can talk more under column. So after understanding the carrier gas, and we said what are the properties of the carrier gas. The carrier gas, why we choose helium, nitrogen, and argon, is that one of them, it must be inert. It must be inert, that is non-reactive to the stationary phase. It should have high density. It should be pure. It should portray high purity. That is 99.9% pure. Then it should be compatible with the detector. Then it should be dry. It should not contain any water droplet and should also not contain any oxygen. That's why some have a sieve. So if they ask you in an exam that state any 4 or 5 characteristics of the carrier gas used in the gas chromatography, 1, it should be inert or unreactive. It should be having high density. It should be dry. It should be compatible with the detector system we use. And it should be thermostable. It should be able to withstand high temperature. And another thing, it should not contain either oxygen in it. So those are the properties. And the last one, which is very key, they should be highly pure. That is 99.9%. So those are the properties of the carrier gas. That is the properties. We have seen the properties of the column and which one is the best. The best one we have said is capillary or open tube column, which is most commonly used. So after understanding this, now the element, which is the containing a compound to be separated, which is volatile, reaches to the detector system. And there are different types of detector system we use in gas chromatography. One of it, which is the most versatile, is mass spectroscopy. Mass spectroscopy is the most commonly used. This is the most and the accurate method of using in gas chromatography as a detector system. The second one we can use is frame ionization detector. We can abbreviate it as FID. This is abbreviated as MS. Then the third one we can use in the detector system is the thermoconductivity detector system, which is abbreviated as TC. Then the fourth one we can use is electron capture detector system. The fifth one we can talk about is atomic emission detector. So these are the 5 types of detector systems which are employed in gas chromatography. And we're going to go ahead and we see when do we use and when do we determine the choice of the detector system. For example, for mass, it is tunable. It can be used for all types of samples being separated, because it is most versatile and tunable to any kind of sample, and is the most accurate method. But how does it quantify different samples? It quantifies them by first bombarding the substances into ionic form. So we ionize them by bombardment, and after ionizing, we select them into fragments. So we form fragments after ionizing the sample. So the first thing is to ionize the sample by bombarding it into ionic compounds. Then we form fragments. And after forming these fragments, they are passed through mass analyzer. So this mass analyzer, it has different sizes. So it is able to measure these compounds according to mass charge ratio, according to mass stroke charge ratio. That is how mass spectroscopy is able to quantify and brings about a readout on a recorder by looking at the mass and charge. Because we have seen it does 2 things. When we bring in a gas, it ionizes it to either become positively charged or negatively charged. Then the second thing is to turn it into fragments. And these fragments pass through, they are ionic fragments, which are going to pass through the mass analyzer and is going to separate them according to mass and charge. And we are able to quantify the graph produced and by looking at its area. That is mass spectroscopy for all type of samples and is the most commonly used and the most stable and accurate. Then the second one is the frame, and as the size frame means we are using burning fire or ignited fire. And whenever we subject, what we are going to do is we are going to join this carrier gas containing a substance to be separated, and we join it with hydrogen and oxygen. So these 2 gases, after combining with the air weight, this gas we are talking about is the air weight. So this air weight, which is containing a substance to be quantified or determined or identified, is going to burn with atmospheric oxygen and hydrogen, because this oxygen is enabling combustion. So this frame that is going to be produced, the frame which is burning, is going to convert substances into either ionic form, whereby they become positively charged or negatively charged. At the same time, it can form what we call electrons. And these are the ones which are going to go into electric field and produce a current. And this current is the one that is produced on the recorder. That is flame ionization. Flame ionization. The flame or the burning fire converting the volatile substances into either ionic, that is positive and negative, or electrons, which are detected as a current within electric field and displayed on the recorder. That is how flame ionization works. And this is best for hydrocarbon compounds. It is most applied to separate or identify hydrocarbon compounds. So compounds which are organic or which are hydrocarbon in nature are best identified using flame ionization. Then the third one is thermal conductivity. This was the first one to be used in gas chromatography, whereby it was depending on the thermal conductivity. It was depending on the thermal conductivity of the carrier gas and that one of the substance or compound to be separated, whereby the conductivity of the gas is used as a reference, so that when we know the graph of the reference gas, which is the element, we can compare it with the one produced by the substance, and we are able to quantify by looking at their difference in conductivity. So we are looking at their difference in conductivity. That is thermal conductivity. And this one is also suitable for, it is universal. It can be used for all types of compounds we want to separate. That is thermal conductivity, the first one to be used. Then electron capture. This one is suitable for samples which contain electronegative functional groups, like halogenated compounds. So any compound which contains halogens, which is halogenated, we can use electron capture, whereby the electrons which are produced by these electronegative substances are captured within the electric field, and they are able to be identified on the recorder. So this one uses halogenated compounds, don't forget about that. Then lastly is atomic emission. But before we go to atomic emission, yes, the atomic emission detector, this one uses plasma. This plasma, I'm not meaning plasma which is blood, but I'm looking at substances, the gas which is containing metal ions or metal which are partially ionized. So we can say it contains partially ionized metal elements. So these elements, they are easily subjected to an atomizer, which is going to make it excited. So they are excited when they can be subjected to either a flame or anything which is burning or which can make them become excited, and they are able to emit photons of light. And these photons of light are the ones that are quantified. So this one is element selective. So what we should not forget about these different detectors is that the mass spectroscopy is universal, can be used for all types, and the most common and accurate method. Flame ionization is for hydrocarbon compounds. Thermal conductivity also universal, basing on difference in conductivity of the carrier gas and the substance to be identified. And then electron capture for electronegative compounds which are halogenated. Then atomic emission for metals or elements which are found in plasma. Those ones which are first partially ionized, so they get excited and emit light, which can be quantified. Hope we are together. Please, if you are enjoying this video, like and share to many others. So as we conclude, we are concluding by looking at application. And this gas chromatography is being applied in pharmaceutical industries, whereby within pharmaceutical industries, it is being used to quantify the chemicals within drugs. You can use it to quantify the amount of ingredients or chemicals in drugs. At the same time, we can use this gas chromatography to identify presence of impurities in drugs. It can also be used to quality control drugs, to see if in drugs there are some chemicals which are not acceptable. And another thing we are using it in the pharmaceutical industry is to determine drug stability, to see if drugs are stable at different conditions. Then lastly is to detect solvent residues. Solvent residues within drugs or any pharmaceutical compound being produced. So this is what we can apply this gas chromatography in the pharmaceutical industry. But apart from pharmaceutical industry, we are also applying this in environmental health, whereby we are using it to determine levels of toxins or air quality in the environment. Toxins like detecting presence of pesticides within the environment. We can use it to quantify them. Then within clinical laboratory, we are using this to quantify different toxins within blood, within breath, within saliva. For example, people who are on drugs of addict like cocaine and other toxins are able to be quantified using gas chromatography. Then in the cosmetic industries, we are also using it to quantify different ingredients within the products which are being produced. Before I produce any cosmetics, like either be Vaseline, it can be a lotion, we can use gas chromatography to quantify different ingredients within this product and determine their purity, at the same time to quality control them. At the same time, we can use it in food industry, whereby food industry we are still looking for presence of toxic substances in food products being produced. So this is how we can apply gas chromatography. In summary, don't forget about the instrumentation, whereby we have looked at the carrier gas and its properties, whereby the carrier gas must be inert, and the most commonly used is helium, nitrogen, and argon. We have looked at the sampler, automatic sampler or syringe, which we use to introduce the sample within the chromatography. And we have seen the injector port. And this injector port is always 50 degrees centigrade higher than the chromatography column. Why? To enable sample to be vaporized by the time it reaches within the chromatography column. And this one we have seen the column having different types, either packed or capillary. But capillary is the most preferred, as we have seen because of these things. And we have said the column is maintained in the oven so that we maintain the high temperature being used, which is between 50 to 450 degrees centigrade. Then we have gone ahead to look at the detector systems and when do we use it and their advantages. We have ended up with application. Thank you so much for learning with us at Medical Sciences. We are always privileged, and the only payment you can give us is by subscribing, liking the video, and sharing it to many others. Thank you so much.